Hi, I'm Logan, one of the managers of MCAT content and curriculum here at Kaplan. In this video, Ari Kim, one of our expert instructors, will take you through what we've identified as one of the toughest passages on Kaplan's free MCAT practice test. This test was designed by Kaplan's question writers and validated by Kaplan's psychometricians to be as representative of the actual MCAT as possible, so you know you're getting a great representation of what you will see on test day. This passage from the Chem-Phys section focuses on chemiluminescence, with questions requiring knowledge of general chemistry, organic chemistry, and some graphical analysis skills. Follow along to see how Ari attacks this passage using Kaplan's passage and question strategy.
Looking over passage 10, the first thing that stands out is the two-step chemical reaction and the acronym CL for chemiluminescence. This seems like a fairly chemistry-centered passage. There's another, more complex-looking reaction described here. At a glance, I'm not really familiar with any of the specifics in this passage, and it does seem pretty dense, so I'm going to use Kaplan's outlining method, making sure to go into a medium depth of analysis in the passage while still budgeting enough time for the questions. In particular, I like outlining relatively dense informational passages because putting relationships and connections into my own words helps me a lot when I get to the questions. Paragraph 1 provides a definition of chemiluminescence. It's when a reaction creates an excited molecule, which must be what this asterisk is indicating. And when that molecule relaxes in the second step, the passage says it gives up light, which must be the H nu here. I usually represent nu, or that squiggly V, using the letter F for frequency, but I've also seen it as nu occasionally. While I don't usually make outlines for reactions or diagrams, I'm going to add those definitions to my outline since I think it might be helpful for later. Paragraph 2 is super short and provides a reason for monitoring chemiluminescence. We can use it to monitor the amount of NO in the air, and since the passage describes NO as a free radical, and I know that free radicals are very reactive and unstable, I'm presuming that NO is probably a bad thing. Paragraph 3 talks about another usage of chemiluminescence with luminol and states that this is chemiluminescence in liquid phase, which now makes me realize that the previous Cl was about a gaseous reaction since it was in the air. While I'm not going to spend a lot of time analyzing this reaction right now, I do notice that this also has light of a specific wavelength as a product. The final paragraph goes into detail about how catalysts are involved in the production of chemiluminescence from luminol, which I can also see is mentioned in this reaction. The second sentence describing the relationship between luminol and catalyst concentration seems like a good MCAT question. Increasing intensity luminescence increases linearly with catalyst concentration, so I'm going to include that in my outline. The rest of this paragraph I'll save for a closer analysis if a question requires it. When looking at question 52, the thing that immediately stands out are those answer choices. They're all colors. The question stem mentions chemiluminescence, so it's possible this is a passage-based question, though I'm not sure. Reading the question more closely, it doesn't actually require passage information at all. It's just asking which color in the answer choices has the highest frequency, so this is a pseudo-discrete question. First thing I need to do is recall a few facts about visible light. While I don't offhand know the frequencies of each visible light color, I know the order of visible light, good old Roy G. Biv. There's actually a few ways to approach this. I know that IR, or infrared, is what my TV remote uses. And on the other side is UV, or ultraviolet. My TV remote doesn't give me a Vern, but UV rays from the sun sure does. Violet then must have higher energy than red does, which is all I need to match to answer choice D. Equation-wise, I do know that energy is equal to Planck's constant h multiplied by frequency, and so the higher the energy, the higher the frequency. But anytime I can solve questions using logic and reasoning skills, that's always a better option for me. I could also solve this question by remembering that the wavelength of red light is longer than violet light and use the inverse relationship in this equation. Speed of light is equal to wavelength multiplied by frequency. That means that the smaller the wavelength, the bigger the frequency. Either way will work. Taking a look at question 53, the first thing I notice are those answer choices, with something about a change in number. The question stem references luminol, so this is probably a passage-based question. Examining the question more carefully, it's asking how the number of sp2 carbons in luminol changes when it turns into 2-amino phthalate, so definitely need to head back into the passage. To help orient me, I'm going to take a quick glance at my outline, and while I don't have it directly in my outline, paragraph 3 references luminol. Now I remember that reaction 2 did have both of those compounds present, so I'm going to head there first. Before I thoroughly examine that reaction, I'm going to recall what I know about sp2 hybridized carbons. While there's a lot of content background behind hybridization, I'm going to keep it short and stick to just what I need for this question. I know that in the valence shell for carbon, it has one s orbital and three p orbitals. In order for me to have sp2 hybridized orbitals, it means I'm leaving one of the p orbitals unhybridized, which is what's then going to be used to form a double bond. Looking at luminol, I can see that there are double bonds around this aromatic ring as well as the carbonyl groups, so counting them up, I have 8 sp2 hybridized carbons. If I were to compare it to 3-amino phthalate, I can see that those specific carbons don't change and no others are introduced. So there are still 8 sp2 hybridized carbons. The other form of 3-amino phthalate is exactly the same, just relaxed, so no need to compare it to the third molecule. No change in carbon hybridization, which makes answer choice B correct. Looking over question 54, it's got a really long question stem that seems to reference some passage information, and no real pattern in the answer choices, though I do see the words reaction rate come up a few times. Digging deeper into the question, it's a reasoning question, asking why it's necessary to know the concentration of O3, or ozone, to figure out how much NO there is using chemiluminescence. These kinds of questions can be tough because they're harder to predict an answer for. I'm not meant to know this as a fact, but instead need to reason through the information in the question stem as well as in the passage. The first thing I'm going to do is reference my outline, and I can see that paragraph 2 mentions using light to measure NO, but a quick look back doesn't give me much more than that. Given the fact that the answer choices reference reaction rate and ozone, I'm going to head to reaction 1 to see what I can dig up. I know that chemiluminescence, which is the H nu in the reaction, is then used to correlate to the amount of excited NO2. That same excited NO2 is what the researchers can use to figure out how much NO was originally present. So I need to figure out why we also need to know the concentration of ozone. I feel like I can get stuck trying to reason this out on my own, so instead, I'm going to go through the answer choices and see what I can eliminate, keeping in mind the connections in the reaction and the importance of ozone. A states that ozone causes free radical formation that interferes with the chemiluminescence being produced, but that's opposite. Ozone is in the reaction that causes the light to be produced in reaction 1. Eliminate. B states that the rate limiting step is the formation of the free radical intermediate from NO, which I presume is the NO2 with the asterisk. That might be true, but that doesn't really seem to explain why it's important to measure ozone concentrations. That would mean that the rate of the overall reaction is only dependent on NO concentrations. Eliminate B. C states that the rate of producing NO2 is second order kinetics. I know from my studies that the order refers to the number of reactants involved in the rate limiting step. If I were to construct a rate law for step 1, like is described in C, it would be rate equals to the rate constant for that step, K, multiplied by the concentration of NO and the concentration of ozone. If it were true that the rate of this overall reaction to produce chemiluminescence was dependent on the concentration of NO and ozone, then this would explain why I need ozone concentrations to figure out how much NO was initially present. Answer choice C is likely correct. Reasoning questions can be tough to just pick and move on, though, so I'm going to take a peek at D as well. D states that NO2 production is first order, which means that there's only one reactant required in the rate limiting step, and I know I need both NO and ozone, so D can't be correct either. I'm going to stick with C and move on. Looking over question 55, I notice that it mentions blood and it's a really long question stem and answer choices, so it's probably a passage-based reasoning question. It's asking for a reason for a phenomenon in the question stem. Why does dried blood produce more chemiluminescence compared to fresh blood? I need to keep in mind that this is not a fact I'm supposed to know for the MCAT, so I'll need to use my content knowledge along with the passage information to select a plausible reason. But first, I'm going to figure out where in the passage to go by using my outline. It looks like the relevant information about luminol is in paragraph 3 and 4. A quick look at paragraph 3 and the reaction doesn't really give me any information about blood. But paragraph 4 certainly does, and I can see the blood component mentioned here. Luminol can be used to detect blood, but I'm still puzzled about the connection. If I look towards the top of this paragraph, though, I can see the link. One of the catalysts for the luminol reaction is iron 2+, which I know from my studies is found in hemoglobin in blood, and it's the iron in the blood that's catalyzing the production of chemiluminescence. If I keep reading into that paragraph, this detail stands out. Organic molecules can complex with catalysts like iron 2+ and make it unavailable. Therefore, it's plausible that in fresh blood, there's some of this organic molecule hiding the iron 2+, resulting in less chemiluminescence. With that prediction, I'm going to head back into the answer choices. A states that iron ions are more available in dried blood than fresh blood because organic ligands in the fresh blood interfere with the iron's ability to catalyze a chemiluminescence reaction, which does match to my prediction. When my prediction matches this closely to an answer, I pick it and I move on. However, in review, it's worth looking at the other answers. B states that the chemiluminescence involves oxidation of luminol and dried blood is less oxidized than fresh blood. If that's correct, the less oxidized dried blood would produce less chemiluminescence and not more like the question stem states. C states that the peroxidase needed for hydrogen peroxide to catalyze the luminol reaction is more available in fresh blood than in dried, but similar to B, that would actually produce the opposite effect to what the question is asking. Also, I don't know of a direct link from hydrogen peroxide and peroxidase to blood like I did with iron, although I suppose it's possible. D states that luminol is more likely to be converted to its product in fresh blood, but again, that would give me the opposite effect. It's the dried blood that gives more chemiluminescence, not the fresh. Moving on to question 56, I immediately notice the graph in the question stem and some numbers that seem to be referencing details about light in the answer choices. Looking more closely at the question stem, it's asking what answer about light is supported by the graph. While the question stem is referencing reaction 2, it doesn't really seem to require information about that reaction quite yet, so I'm going to start with examining the graph. Along the x-axis, I see peroxidase concentration in nanomolar and chemiluminescence intensity percentages on the y-axis. The interesting thing about this bar graph is its almost perfect linear correlation. For example, at 10 nanomolar peroxidase, there's 10% chemiluminescence, and that relationship is true for all peroxidase concentrations. The value of the concentration of peroxidase is the same value for the chemiluminescence percentages. With that trend, I'm going to take a look at the answer choices. Looking at A, it states that there are 3 times as many photons per second at 30 nanomolar as at 10 nanomolar. I know from my studies that brightness of light, otherwise known as intensity, is proportional to the number of photons detected per second. Since 30 nanomolars is 3 times larger than 10 nanomolars, the graph does support a 3 times relationship with the number of photons per second, making answer choice A correct. B and C make statements about the frequency and wavelength of light being emitted and it changing between concentration, but that's not what's changing with intensity, it's the number of photons. Changing wavelength and frequency would change the type of light being emitted. D is interesting though. It has a very similar scenario compared to the correct answer. 4 times as many photons at 40 nanomolar as at 10 nanomolar is the same linear relationship I saw in answer choice A. However, D includes this additional component about how the number of photons emitted was over the course of the reaction. And I know that it's not over the course of the reaction, but per second. If D was true, then the number of photons per second would be the same at 40 nanomolar and at 10 nanomolar.